Okay, so this is the second video I'm making, which uses the definition of the derivative in order to solve problems regarding, I guess, velocity or rate of change, right? We have, again, what is the derivative? So we have like a function, and we try to see how quickly is the function when you zoom into 2 points over here, but they're infinitely close to one another in a sense. How quickly are we changing? Is the y coordinate changing in terms of x? So what's the change in y in terms of the change in x, right? So the rate of change of our function, and that's pretty much what we're trying to do. And we're using the concept of a tangent line, a line that just touches that point, to explain how quickly what the rate change is. So now I'm going to do problem 15 on page 120, which says the displacement in meters of a particle moving in a straight line is given by the equation of motion f of t is equal to 1 over t squared, where t is the measure in seconds. Find the velocity of the particles at time t equals a, t equals 1, t equals 2, and t equals 3. So again, I'm going to just use the definition of the derivative, or what we use to find tangent lines. H goes to 0. And I'm just going to make this for arbitrary t. So t plus h squared minus 1 over t squared over h, which is equal to t squared minus t plus h squared then we have t plus h squared times t squared times h, right? That's what this is equal. The limit as h goes to 0. So up here we get, so t plus h times t plus h is equal to t squared plus 2th plus h squared. So this is equal to the limit as h goes to 0 of t squared minus t squared minus 2th minus h squared, right, all over t plus h squared times t squared times h. So now these cancel, and we get, this is, I'm going to take out an h, this is the limit as h goes to 0 of h times negative 2t minus h over t plus h squared times t squared times h. These h's cancel. Now as t goes to 0, this becomes negative 2t over t squared times t squared, which is t to the 4th. This is equal to f prime of t, or the derivative for any given t, right? And it can finally also be written as negative 2 over t to the 3rd. So now we want to find this for t is 1, t is 2, t is 3. We know that f prime of t, or the rate of change of our function f, is going to be equal to negative 2 over t to the 3rd. So the rate of change of our function at 1 is just negative 2 over 1. The rate of change of our function at 2 is just negative 2 over 2 to the 3rd. The rate of change of our function at 3 is just negative 2 over 3 to the 3rd, and so on. So that is how quickly our function is changing. So now I'm going to do problem 17, and it requires me to draw a picture. So we have function goes something like this, then down, up, and then like that. So this is 2, -1, 0, 1, 2, so on. And we are given, so we have 0, g prime of -2, g prime of 0, g prime of 2, and g prime of 4. And we are asked to put these numbers in increasing order. So let's first find which one of these is negative. So if we look at, this is negative, if we look at g prime of -2, we have a pretty sharp movement upwards. So the rate of change of this function at -2 is positive, and it's pretty big. So we can put g prime of -2 somewhere over here. Definitely greater than 0. Where over here at 0, at g prime of 0, the rate of change is negative, right? We're changing, we're high, and then we go lower and lower and lower. So we're going from a high place to a low place, so the amount that we're changing, the rate of change, is negative. So we can put g prime of 0 is less than 0, because the rate of change over here is negative, is less than 0. So that is for 0. For 2, our rate of change is positive, but it does not look as positive as for -2. So we're going to put g prime of 2, let's say, over here for now. And then for, so we have this, we have that, we have that, we have that. So for g prime, this is what, 4? So at 4, our function kind of looks something like this. So the rate of change is positive, but it's also not very positive, because it's not very steep. So it's going to be something like this. So that's how this is putting them in increasing order. This is negative, then we have 0, we have a positive, small positive number, slightly larger positive number, and then a very large positive number, because the function is very steep here, so the rate of change over there is very... Okay, so I'm going to do, for problem 18, I'm going to do part A, because I'm not sure what part B is asking, because it's asking about an fx, and they never tell you what fx is. So, maybe... Oh yeah, no, I'll also do part B. I figured out how to do part B. So, okay, so we have y equals g of x, and for x so we wanted x equals 5. If g of 5 is equal to -3, and g prime of 5 is equal to 4, we want to find the tangent line at 5. So we know, so we are looking at the point 5 comma -3, right? Because, sorry, it's not 5. We're looking at the point 5 comma -3, because this is the y coordinate. And so when we write it, we write y equals, we write y minus -3, which is +3, equals m, the slope, but we know what the slope is of 5, it's 4, times x minus 5, or in other words, y equals to 4x minus 20, and then minus 20 minus 3, so this is minus 17, or sorry, minus 20 but minus 3, so no, sorry, this is minus 23. That's the answer for part A. For part B, we're given, this is actually an interesting question, y is equal to f of x, and we say if the tangent line at the point 4 comma 3 on x of x on f of x passes also through the point 0 comma 2, we want to find f of 4, and which is obvious. F of 4 is clearly 3 because that's the point that we're dealing with, but the interesting question is f prime of 4. How do we find the slope? Well, that's easy. We just find the slope between these 2 points because we know that the tangent line passes through this point and through this point. So we just have to find the slope of the line that passes through those 2 points, which is 3 minus 2 over 4, which is 1 over 4. So this is equal to 1 over 4. Basically, we're working backwards from the information that we're given, and given that we understand what f prime of 4 means, we understand that this means the slope of the tangent line at 4, we can figure out the rest. We can figure out what it is, because all we need to do is find the slope of this line that we're given. Okay, so the next problem is problem 19. Sketch the graph of the function f. So we have f of 0 equals 0. F prime of 0 is equal to 3. F prime of 1 is equal to 0. And f prime of 2 is equal to negative 1. Right? So here we have our thing, and we know that f of 0 is 0, and f prime of 0 is 3. So we're even increasing a little more than that. Let's try to draw this again. So f of 0 is 0, and at 0 we're increasing at a rate of 3, and at 2 we're decreasing at a rate of negative 1. So let's say we're doing something like that. At 2 we're decreasing at a rate of negative 1. And at 1 we're not the rate of change isn't moving. So a function that does something like this is pretty much following our rules, right? So at 0 it's 0. F prime, yeah, at 0 it's 0, but the f prime of 0 is 3. At 1, it's the rate of change is not changing. The tangent line would have slope 0. And and at 2, we're decreasing at a rate of negative 1. So that's how our function would look. Okay, so the next problem that we are going to look at is a similar problem. It's problem 20. So sketch the graph of the function g for which g of 0 is equal to g prime of 0 is equal to 0, and g prime of 1, negative 1, is equal to negative 1, and g. Learning how to sketch these graphs, I think, is one of the most important things in Calc 1, simply because of finding derivatives and limits, all that computers can do, but understanding what derivatives are, understanding what tangent lines are, that all comes about from looking at these type of statements and trying to figure out how a graph would look if you're given these statements. What kind of graph satisfies these statements? That gives you the intuition of what derivatives are, right? Taking a derivative, a computer can do that. Taking an integral, a computer can do that. Finding a limit, a computer can do that. None of that is like, you're just learning how to do that in order to understand the concepts. This is the concepts. These are what you are trying to understand. So for g of 0, and also obviously understanding how functions work, what you plug in, what you get out, what a Cartesian plane is, stuff like that. But anyway, that you should get from pre-calculus, I guess. So g of 0, it's g prime 0, 0. So at 0, we're at 0, and we're not, our rate of change is 0. We're not changing. So it would look something like that. And negative 1, so here we are at negative 1, our rate of change is negative. So let's say we're going something like this. At 1, our rate of change is positive, so we're maybe doing something like that. And at 2, our rate of change is also positive, but less so. It's positive, we're going up, we're changing in this type of direction, but it's not as steep as the rate of change at 1, because at 2, our rate of change is just 2. So now let's just draw a graph that satisfies this. So a graph that does something like this, and then starts going up and goes up like that. So right at 1, we have a negative rate of change. At 0, we're not changing at all. At 1, we're changing positively. We're going up and quite steep. And then at 2, we're not as steep, but we're still going up. So that's how that function, one way to satisfy that function. Okay, so we already did a lot of problems, like problem 21 and problem 22. And also problem 23, problem 24, and problem 25. So we'll do another one of these, I guess. Let's just do problem 23, and then maybe problem 25, something like that. And we're not going to do the graphing part of problem 23, obviously, but it looks like a slightly difficult problem with some algebra, so maybe it'll be fun, I don't know. So we have f of x is equal to 5x over 1 plus x squared, and we want to find f prime at 2 and use it to find the equation of the tangent line to that curve at the point 2, 2. So we've done conceptually, we know everything that we need to do. We need to find the derivative using the definition of the derivative, and then plug in 2 to that derivative, or we're just going to take it in terms of 2. We're not going to find the general derivative for f of x. And then using the equation for a line, we'll just finish it that way. So this is the limit as is h. As h goes to 0 of 5, 2 plus h over 1 plus 2 plus h squared minus 5 times 2 over 1 plus 4 all over h. And this is going to equal, let's see, so this is going to equal to 5 times 2 plus h times 5 minus 10 times 1 plus 2 plus h squared, right, finding the common denominator, over 1 plus 2 plus h squared, h squared, all of this times 5, and then times h. Okay, so this is going to equal, so what is 2 plus h squared? It's equal to h squared plus 4h plus 4. So this is going to equal, so this is the limit as h goes to 0. It's going to equal the limit as h goes to 0 of 10 times 5, 50 plus 10h minus 10 plus okay, plus, but then there's a minus for the 10, so we're going to have minus 10h squared minus 40h minus 40, right, all over 5 plus 5h squared plus 20h plus 20, yeah, 20 all times h. So now let's just delete this and continue. So this is equal to the limit as h goes to 0. Okay, so we have 50 minus 10 minus 40, so the 50s, that cancels. And okay, I think that's it. Kind of, I mean, we end up with 30h, but okay, that doesn't matter. So let's take out the h's, so we get an h, 10 plus 10h minus 30 over h times 5 plus 5h squared plus 20h plus 20. These h's cancel, and then as h goes to 0, this becomes 10 minus 30, so 20 over 5, this vanishes, plus, so this becomes 25, so it becomes 20 over 25. Sorry, it's 10 minus 30, so it's negative 20 over 25, or in other words, or negative 4 over 5. Okay, and then we use y minus 2 is equal to negative 4 over 5 times x minus 2. Alright, yes, and then we solve for it, so we get y equals negative 4 over 5x plus 4 times 2 over 5 minus 2, whatever that is, oh sorry, plus 2, whatever that is. So that is how we do that problem. So now let's do problem, well, actually, so let's do problem 25. Actually, we pretty much already did a lot of problems, like problem 25 until 30, and then problem 31 until 36. It's just a lot of algebra. And then problem 37, 38 we did. Problem 39, those don't seem interesting. 41, 42, none of those seem interesting. Problem 43, again, you take the derivative, or find the secant lines, take the derivative, so on and so forth. Does not look very interesting. So let's actually look at problem 45, just because this is more about intuitions. The cost of producing X ounces of gold from a new gold mine is C equals F of X dollars. So we want to know what's the meaning of the derivative over here. And the meaning of the derivative is the rate of change of how much it costs to produce gold with respect to how many ounces of gold you want to produce. So maybe the derivative, maybe the function goes down, meaning the more you try mining, the less the less you need to pay per ounce, right, or something like that. So the derivative might be going down. So yeah, something like that. And the units is dollars per ounces, the amount of dollars that it costs per the amount of ounces. What does the statement f prime of 800 equals 17 mean? Well, it means that if you want, at just f of 800, you're asking how much would it cost to produce 800 ounces of gold. But if you're saying f prime of 800 is 17, you're saying, listen, the amount of money that it costs per ounce of gold, the amount that it's increasing instantaneously at 800, meaning the rate of change of the amount that it costs to produce a certain ounce, the rate of change of that is 17. Do you think the value of f prime of x will increase or decrease? Well, it will probably decrease, because that the more you mine, the less it probably costs per ounce that you want to mine. So if you just want to mine 1 ounce, putting up all the equipment, getting everything together, it might already cost a lot. So the amount of money per ounce is a lot. But as you start mining more and more, the production might go up, meaning, to mine 800 ounces will probably always be bigger than mining 700. But the amount that it will cost to mine per ounce, the amount of money you're going to have to spend per ounce, is probably going to go down. So your function is probably going to look something like this, right? So when you just start, it's pretty costly per ounce, right? This is, let's say, the amount of ounces that you want, and this is how much it costs, right? So if you want to get 10 ounces, it will cost a certain amount. If you want to get 100 ounces, it's going to cost more. But then if you want, 1,000, it's not going to cost that much more. It's not going to cost that much more between 100 and 1,000. The rate of increase is going to be much bigger between 10 and 100. This graph might not be like 100% how it would look, but we can assume that it's going to look something like that. Do you think the value of f prime of x will increase or decrease in the short term? What about the long term? So I'm not sure what it means by short term or long term. Doesn't mean with relative to time, because we don't have time here. I do believe that f prime of x will always be increasing, but it will be increasing in a slower and slower rate. It's never going to be negative. Yeah. Fine. Let's look now at problem. Let's look now at problem 46. The number of bacteria after t hours in a controlled laboratory experiment is f of t is equal to n. That's the number. So we want to know, what is the meaning of the derivative of f prime of 5? Well, the meaning of the derivative is that after 5 minutes, the rate of change of the bacteria, the rate of change of the number of bacteria, basically tells you the rate of change of the bacteria after 5 hours, how much they're increasing, how much they're decreasing, what's the rate of their change 5 hours later. Okay, what are its units? So the units are going to be the number of bacteria per hour. So now we're asked, suppose there's an unlimited amount of space and nutrients for the bacteria. Which do you think is larger, f prime of 5 or f prime of 10? So f prime of 10 should be much larger, because that we're going to start out and we're going to start out like this, and we're going to increase very, very quickly. And if the bacteria have all the room that they want and all the food that they want, right, you're going to start with one bacteria and it's going to split to 2, and then these are going to split to 4, and next thing you know, 5 minutes later you might have 100, but 10 minutes later you might have thousands of bacteria, and the rate of change 10 minutes later, meaning the amount that we're going to change from, let's say, 10 to 10 plus an infinite second later, is going to be very big, versus the rate of change of 5 might not be as big, because you're going to only have 100 bacteria, which are about to turn, let's say, into 200 bacteria or something like that. So that's why if you have as much room as you need, then f prime of 5 is going to be much smaller than f prime of 10. But if the supply is limited, would that affect the conclusion? Of course, meaning the bacteria might explode at 5, become a lot, but then run out of food, not have any more food, and then they might all die. And by the time we reach f prime of 10, so maybe f of 10 would just be 0, meaning there'll be 0 bacteria left. So f prime of 10, if there are no bacteria, you cannot get any more bacteria, they're all dead. So that will also be 0. So obviously that's going to change the conclusion. So let's look at problem 50. The graph shows the influence of the temperature T on the maximum sustainable swimming speed S of salmon. What is the meaning of the derivative S prime of T? What are its units? So the meaning of S prime of T is the measure of change, we're trying, or the rate of change of how sustainable the speed of our salmon are per unit of temperature. So if you increase, how quickly does the speed increase or decrease as we change the temperature, meaning the speed might increase as you change the temperature, meaning if we're going towards a better temperature for speed, whatever that means, then the rate of change might increase, and if we're going towards a worse one, then the rate of change might decrease, meaning, the units again are the amount, it's the speed, so something, let's say, like centimeters per second over the temperature, or how, so on, and estimate the values of f prime. So I don't know, the graph kind of looks something like this, and S of 15 is somewhere there, and S of 20 is somewhere, let's say, here. So at S of 15, if you increase the temperature a little, if you increase it, the speed at which you will be going would be faster. The rate of change, or rate of so you increase the temperature a little, and then the rate of your speed over time, the amount that you travel over time, is going to increase. And over here, if you decrease the temperature, you'll increase your speed, or the sustainable speed, and if you so on. Okay, we're going to look at problem 51. Determine whether the derivative exists of f. So the derivative of f prime of 0 exists, and the first question is for f of x equal x sine 1 over x. If x is not equal to 0, it's equal to 0 if x is equal to 0. So let's write down the definition for our derivative, and I'm going to use the original definition because it's going to make things easier. And basically what we want to see is whether the limit exists. So we're going to take the limit, right, as x goes to a, in which case, in our case, a is 0, of x sine 1 over x minus f of a, which in our case is 0, because that for f of a we're going to choose this, so it's 0, over x minus, so x minus a, which in our case is 0, so this is the same as just sine of 1 over x, and we know that the limit for sine of 1 over x does not exist because that, so we definitely can't plug in 0, we're dealing with a limit over here, and sine of x looks something like this, right? That's whatever, how sine of x looks. So sine of 1 over x is like basically taking the following two things, sine of plus infinity and sine of minus infinity, and this is happening as x approaches 0, right? As x approaches 0. Meaning because that, right, we know that 1 over x approaches plus and minus infinity. So if we look at our graph, the sine is going to do something like this. As we're approaching 0, the sine is going to start oscillating an infinite amount of times backwards and forwards, bounded over here by -1 and by 1. Right, and it's going to start oscillating an infinite number of times because that as sine is getting closer and closer to infinity, when we change a little bit, you know, from 1,000,000 to 1,000,000 of 1 and 1, sorry, when we change a little bit on the x-axis, we'll be changing this number, right, the number that's approaching infinity, tremendously, because 1 over x starts, you know, gradually, and then it really shoots up to infinity, and it starts gradually and really shoots down to negative infinity. So when we go, let's say, from 0.01, which is close to 0, and we go, let's say, to I don't know, a close number but smaller number than it, I don't know, 0.009. When we do this, this number over here, right, sine of 1 over 0.0099 is going to be drastically different than sine of 1 over let's say okay, something's going on down here, I'm going to change, then sine of 1 over 0.01. It's going to be drastically different, but the idea is sine is bounded, and it's going to start jumping back and forth as this number is changing drastically, because this number and this number are very different, and so it's going to start jumping back and forth very quickly. But it's not going to approach 0, it's not going to be approaching -1, and it's not going to be approaching 1. It's going to go to all of them, and it will touch them and hit them an infinite amount of times. And because of that, sine of 1 over x, the limit for sine of 1 over x does not exist. And therefore, the derivative, which is defined in terms of the limit, also doesn't exist. So the derivative for our first problem, for exercise 51, does exist. Let's look at our second problem. So our second problem asks us to find the derivative, again as f for f prime of 0, to see if it exists, for f of x equals x squared sine 1 over x if x does not equal to 0, and 0 if x equals to 0. Again, because of this, I'm going to be using the original definition for the limit because it makes things much easier. So we have the limit as x approaches 0, because that's where we want to find a derivative of f of x, which in our case is x squared sine of 1 over x, minus f of 0, right, which if we just had this part, that would not be defined, but because that at x equals 0 we're dealing with 0, we can just write -0, because that's f of 0, right? F of 0 equals 0 over x minus 0. And then these are going to cancel, so we're going to be dealing with the limit as x approaches 0 of x sine 1 over x. And now this limit does exist, and we can use the squeeze theorem to show that it exists, right? Again, what does the squeeze theorem say? Let's just write it out. It says that if we have h of x is less than or equal to f of x is less than or equal to g of x, and we have the limit as x approaches some number a of h of x is equal to the limit as x approaches a of g of x is equal to L, then the limit as x approaches a of f of x is also equal to L. That's the theorem. So in our case, we have f of x equal to x sine 1 over x. And I've seen people make the following mistake a couple of times, which is not good, and I'll show how to correct it a little. So we know that we want to squeeze this, so we take -1 is less than, we know that sine is always bounded by the 1 and -1, so this is less than sine 1 over x, which is less than 1. And then the following I myself have made the mistake of saying, okay, so then -x is less than x sine 1 over x, which is less than x, right? And so we bounded this function by -x and x, and as we take the limit as x goes to 0 of -x is equal to the limit as x goes to 0 of x is equal to 0, so therefore the limit over here is 0. And the limit is 0, but this statement right over here is incorrect. And the reason you can't make it, first thing, obviously, graph it, and right, sine of 1 over x is going to do something like this. Well, you hit 0 over here, x is going to go like that, and -x is going to go like that. Clearly, they're not, the claim made over here is clearly not true. And the reason you cannot go from here to here is because that when you multiply everything by x, sometimes x is positive and sometimes x is negative. So you cannot just keep the inequalities this way. Sometimes, let's say if you're multiplying by x which is negative, let's say look at the x's for -1, then really this statement will be negative times -1, and you would have to flip the inequality to make this statement true. So you can't just keep these inequalities for the x's that we chose. So this statement is false, right? If, for example, you add x squared here, then you can bound this, you can just put here x squared, because x squared is always positive, and you won't have the problem that I mentioned. But now, so what are we going to bound this by? Well, we can do something a little similar. We can say, listen, this is bounded by the absolute value of x, which is less than the absolute value of x sine 1 over x, which is less than the absolute value of x. So we're going to squeeze this by the absolute values of x's. The only problem with this is that the absolute value over here of x is not what we want. We want x. But we can make the following claim, which isn't very rigorous, but is true. First thing, it's also true that negative absolute value of x is less than x sine 1 over x is less than x, absolute value of x. But we can say, listen, the absolute value of sine of 1 over x, so when you take this, is pretty much equal to x sine 1 over x when x goes to 0. I mean, in fact, they are equal, because that, as x goes to 0, worst case scenario, so if you have a negative here, so this will be a, let's say, if it's a positive number, this is a positive number, then these are going to be, sorry, if this is negative, and this is negative, this is positive, but it's a really small positive number. I mean, this is a really small positive number, negative number, so changing it to a really small positive number should not really change this equality, right? Taking a really small negative number and changing it to a really small positive number, and then multiplying it by something should not really change the equality. Obviously, 1 over x is vastly different than 1 over the absolute value of x as x approaches 0, but multiplying it should not make a difference. So anyways, we have this, and so we have the limit as x goes to 0 of negative absolute value of x is equal to the limit as x goes to 0 of the absolute value of x is equal to 0, So the limit as x goes to 0 of x sine 1 over x is also going to be 0. And so we have a derivative. So f prime of 0 is equal to 0, which is very interesting. Okay, so we have finished this section. So now we go on to the next section. And I guess I have like 15 minutes till we reach an hour, and I prefer to upload this when we reach an hour. But I don't really want to go through examples in this chapter. So maybe I'll go through some examples, but I also kind of want to start talking about the definition of what's going to go on next with the notation. So we know that the derivative f prime of x, we have talked about the definition for it. People also write it as y prime, or my favorite definition is dy, the change in y over dx. And this comes because that the derivative by its nature is asking for a rise of for the change in y over the change in x. And then we're taking this, and we're taking the change in y goes to 0, and the change in x goes to 0, and we're asking, okay, so what does this equal? And right, and we basically have like 0 over 0, but because that we're taking the limit, we can kind of do it, and we get some number. So dy over dx symbolizes an infinitely small y in terms of an infinitely small x, and it asks for the number that equals. Or we could write, if we have it in terms of a function f of x, but we don't want to use the prime, we can write it in terms of df over dx. All right, that's another notation, or d over dx of f of x, meaning the change of f of x in terms of a really small x. How much is f of x changing in terms of a really small x? Or just the derivative of f of x, or the derivative in terms of x of f of x. And this becomes useful when you start learning partial derivatives, I guess. But not really. And so we can look at like the next step. Let's say we have a derivative. So we have f prime of x, and we want to take the derivative of that derivative, the rate of change at which the rate of change is changing. We write f prime of x, and this is also equal to d squared of y over dx squared. It's also written as this, because basically we're asking for the rate at which the function dy over dx is changing in terms of x. So that's something else that we can do. So, because of a lot of the problems in this section of problems that we have done already, I feel like I should just maybe spend 20 minutes going through different problems, and then we'll be done with this section. I don't want to go through this again. So let's just look at problem 1. Let's look at problem 1. So we have a graph that looks something like this, and that 1, 2, 3, so it goes like this. Then over here it does something like that. Then it goes down to 0, goes down, this is at 1, then it goes up, so this is 1. This is -3, this is -1, and this is whatever. And we're asked to find, so let's look first at AF. So 1 is f prime of 3. So at 3 we have some small positive change. It looks kind of like maybe 1. So now let's look at f prime of -2. Well, at -2 we also have a small positive change, and it also kind of looks like 1. Or maybe less than 1, I don't know, half, something like that. So let's now look at, that's -2, so C asks us for f prime of -1. So at -1, our change, we're not changing it at all. So this is going to be 0. At C, D asks us for f prime at 0, well, at 0 we have a pretty sharp decrease. I'm going to say that that's like -2. So -3 maybe. And then, okay, that was D. E is asking us for f prime of 1. So at 1, again, it looks like a 0. We're not changing at all. F is asking us for f prime of 2. Well, at 2, so at 2, we are somewhere here, and we have a small increase. I'm going to say it's, I don't know, a half. That's the increase, let's say. Okay, and G is asking us f prime of 3. We already did f prime of 3. Okay. Oh, sorry. So this is f prime of 1 is f prime of -3, and that's more like 2, I would say. And then for 3, this is more like 1, actually. So, yeah, something like that. Let's look at the problem. It's very similar. So the second problem, we have our function. It goes down. It goes like this, and up, and down. The rate of changes are a little faster and slower than I drew, but okay. And then this is 0. This is 1. Okay, so let's find f prime of 0 is some negative number. I don't know, -1. Then f prime of 1. Well, that's 0. It's not changing at all at 1. Then C is f prime of 2. Well, at 2 we have a change. I would say it's about 1. Okay, and then f prime of 3. Well, at 3, 1, 2, 3, still a change, more like 2 at this point. So then f prime of 4. So at 4, it looks like 1, 2, 3, 4. It looks like, so this is 4. So it's 0 at 4. And then f prime of 5 is negative. So 0, f prime of 5, some negative number, let's say -1. Okay. I can't do problem 3 because even though it's a very interesting and important problem, it would require a lot of sketching stuff, which I'm already a very good job at. Can't do problem 4, can't really do problem 5 or 6. Problem 15. Problem 15 basically uses the definition of derivative. We know that how x squared looks, so it's like something like that. So just use symmetry and then verify what you're doing with the definition. I'm not going to do 15 or 16. Problems 17 to 27 are pretty much, we did a lot of them already. I'm not going to do any of those. So I think I'm going by doing problem 43 and then maybe problem 52, and that's going to be it. So problem 43 asks us, use the definition of the derivative to find f prime of x and f prime prime of x. So the second one, and then I'm not going to graph them, but f of x is going to equal to 1 plus 4x minus x squared. So first we're going to use the definition of the derivative. So it's the limit as h goes to 0 of 1 plus 4x plus h minus x plus h squared minus 1 minus 4x plus x squared over h. Then we have x plus h times x plus h. It's going to give us x squared plus 2xh plus h squared. So this is equal to the limit as h goes to 0 of 1 plus 4x plus 4h minus x squared minus 2xh minus h squared, right? And then this minus, I'm not going to write it, but this minus, this one, negative 1 and this 1 cancel. And this negative 4x and this 4x cancel. And this x squared plus x squared and this x squared cancel. I'm going to have this over h. I'm going to take out an h, so I'm going to get the limit as h goes to 0 of h for minus 2x minus h over h. These are going to cancel. As h goes to 0, this becomes, so f prime of x is 4 negative 2x. Yes. And then, so that's what f prime of, so let's write that down. F prime of x is equal to 4 plus 4 minus 2x. So let's look at it prime at x. So again, we're going to do the same thing. The limit as x goes to 0, sorry, h goes to 0, 4 minus 2 x plus h minus 4 minus 2x over h. These 4's cancel, and then this 2x, sorry, this becomes plus, this 2x, negative 2x, and 2x cancel, and this just becomes a negative h, 2h. So this becomes just negative 2h over h. The h's cancel, it becomes negative 2. So that's what h prime of x is. So the problem I'm going to do is problem 52. And we're given just slightly new definitions. The left hand and the right hand derivatives of f at a are, and you can kind of guess, so this is the left hand derivative of at a is equal to the limit as h approaches 0 from the left of f of a plus h minus f of a over h. The right hand derivative f prime plus a is equal to the limit as h approaches 0 from the right of f of a plus h minus f of a over h, right? Kind of intuitive. So now we're given function f of x equals 0 if x is less than or equal to 0, 5 minus x if x is between 0 and 4, and 1 over 5 minus x if x is greater or equal to 4. So we're asked first to find f prime from the left of 4 and f prime from the right of 4, right? So by definition over here we're going to have f prime from the left of 4 sorry, we're doing all of this at 4, so x is not 0, x is 4. that's my mistake. So this is the same as, okay, let's try this one again. 1 over 5 minus 4 plus, minus h minus 1 over 1, so minus 1 over h. So this is going to be the limit as h goes to 0 of, so this over here is just 1. So this is going to be 1 minus 1 minus minus 1 times 1 minus h over h, which is equal to the limit as h goes to 0 of 1 minus 1 plus h over h. These cancel and this becomes 1. So the limit from the right is 1 and from the left is 1. So the actual derivative doesn't exist because that the limit from the right and from the left are different. Okay, now sketch the graph. I'm not sketching the graph. Now the question is, where is f discontinuous? So let's write down what f of x is. F of x again is 0. If x is less than or equal to 0, it's 5 minus x. If we have x's between 0 and 4, it is 1 over 5 minus x if x is greater or equal to 4. So the discontinuities might happen at 0 or at 4. So let's see at 0, right? Let us, so at 0 we can just plug in 0. So basically f of 0 is just 0. And now we want to look at the limit as x approaches 0 from the right of f of x, because from the left it's also going to be 0, because from the left x is less than 0, so we're going to use 0. The right, well, this is equal to the limit as x approaches 0 from the right of 5 minus x, which is going to be 5. So that's definitely a discontinuity. Now let's see if there's also discontinuity of 4. So there's a discontinuity here. Okay, so at 4, let's look, f of 4 is equal to 1 over 5 minus 4 is equal to 1, right? Because we just plug in 4. And so we need to look at the limit from the left, because the limit from the right is going to be the same thing. So the limit as x approaches 4 from the left of f of x is equal to the limit as x approaches 4 from the left of 5 minus x is equal, plug in 4, 5 minus 4 is equal to 1. So there is no discontinuity at 4, as we already showed the derivative at 4. We don't have a derivative of 4, so it's not differentiable at 4, but the question is it differentiable at 0? So the derivative at 0 is clearly 0, and the derivative if we approach from the left, so it happens when we approach from the right. So what's the derivative of 0 when we approach from the right? So that's the limit as h approaches 0 from the right, and now f of us is 5 minus x. So this is 5 minus x plus h minus 5 minus x over h, which is equal to, so 5 and 5 cancel, and we get negative x minus h minus x, which is plus x. So these cancel, we get a negative h over h. These cancel, and we get a negative 1. So the derivative is negative 1, and if from the left is 0, so the derivative doesn't exist. And I think, yeah, we're going to stop the video here. So now we're gonna, next video is gonna get to the more interesting stuff of actually using differentiation formulas, and we're just gonna go through a bunch of derivatives, not using the definition of the derivative, but using rules that we're going to learn. Okay, hope this was helpful.